There are several common notational extensions to Backus-Naur Form that make it easier to write. These conventions are known as extended BNF, and although they do not change the expressive power of grammar in any way, they do make the grammars easier to describe. The first extension is optional components. Here is a rule for defining an if statement with an optional else clause. This is a rule using standard BNF rules. If a Boolean expression, then a statement, or the second option, if a Boolean expression, then a statement, else another statement. Note that this rule will result in an ambiguous grammar, as was shown in the previous video. However, for the sake of our current discussion, what matters is that the first part of the right-hand side, this rule there, is the same as the first part of the right-hand side in the second rule. They each start the same. Extended BNF allows us to rewrite this rule as a single compact rule as follows. This second rule has if Boolean expression statement, and then inside of square brackets we have the else and then statement portion from the previous rule. Entities inside of square brackets are considered optional. Therefore, these two rules are identical, but use different notation. Another extension to BNF is the use of curly braces to indicate that part of a right-hand side may be repeated 0 or more times. For example, let's define a simple mathematical expression that can only consist of addition operations using both standard BNF and extended BNF. Both grammars use a non-terminal symbol term that can be either a valid identifier in the language or a numeric literal. As before, these elements could be their own non-terminals, but we will treat them as terminals for the sake of this example. The items in curly braces could be completely absent, which would correspond to the second right-hand side of the rule using standard BNF. We could also have an arbitrary number of this part of the rule repeated over and over again. This is represented using recursion in standard BNF. So extended BNF effectively removes the need for this type of recursion in the definition of our grammar by replacing it with a form of iteration. Note that because extended BNF is not fully standardized, there are alternate notations that mean the same thing as this EBNF rule above. A popular alternative, which is also seen in regular expressions, is the clean star. This rule means the same thing as the last two, but uses parentheses and a star. This star here is the actual clean star, where this is the last name of the person who invented it. The parentheses are only used because the plus and the term need to be grouped together. It's the combination of these items that is repeated. The parentheses can be left out if only a single entity is being repeated, such as a digit in this example. Here we have a positive integer represented as some non-zero digit followed by an optional and arbitrary number of regular digits, and there's the clean star. So non-zero is 1 through 9 with the vertical bar indicating selection or choice, and a digit is either a 0 or a non-zero. This example actually leads us to another common extended BNF extension, which allows multiple choice selection as is done here, but we will do that selection in a nested fashion within the right-hand side of a rule, as in the following. Here, the right-hand side of posint starts with a non-zero, and then after that mandatory non-zero, we have this section in parentheses, which can either be a 0 or a non-zero repeated an arbitrary number of times. This rewrite allows us to eliminate the non-terminal symbol for digit, which was used there. Of course, these two grammars mean the same thing. We could go further and also eliminate the non-zero, but as you'll see, the rule becomes more cumbersome and repetitious than helpful at that point. This version of the rule has fewer rules in it, because we no longer have a non-terminal for non-zero, but isn't really any easier to read. It does mean the same thing though. First, we have to pick a 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's a non-zero. And then we pick a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, 0 or more times. There is yet another symbol we can use if we want to force there to be a certain number of occurrences of a given symbol. Here is a rule describing scientific notation. For example, plus 1.57 e to the negative 7. So this is notation for representing the value 1.57 times 10 raised to the negative 7. This grammar could also represent a negative value, such as negative 5.0 e to the 532. So this would be negative 5 with 532 zeros after it. So how is this represented in this grammar rule? Well, we have a selection indicating we have to start with either a plus or a minus, and so these are terminals. Then we have exactly one digit, and that digit can be a 0, as in plus 0.327 e to the negative 6. Now generally we prefer not to start off with a 0 like that. We would only have a 0 if the overall number is 0, but we'll let it slide for this grammar right now. Notice that we then have a digit with a plus sign, and this plus sign is not a terminal. This plus sign is a feature of the extended BNF grammar that says that we repeat the digit symbol at least one, but potentially more times. So we mandate that there is a digit after this decimal point, at least one, and we could have more if we want. Then we have E, which is a terminal. Then we have either a plus or a minus, those are both terminals, and then we either have 0 or some positive integer, where of course the positive integer could consist of multiple digits, as we saw in the previously defined rule. Of course, in this rule, it isn't obvious that this plus here is a special symbol as opposed to a terminal symbol. That's why when we have all of these special symbols in the complicated extended BNF rules, we sometimes want to designate which symbols are the terminals and which symbols are part of the grammar by putting them in quotes, like so. In this version of the rule, all terminals are in quotes. So the plus and the minus here are terminals, the decimal point here is a terminal, but this plus sign is a grammatical symbol representing that this digit must be repeated at least once and potentially more times. Then we have the remaining terminals, the E, plus, minus, and the optional 0 here. Still, despite the fact that this does clarify what the grammar means, you won't always see the single quotes used, particularly in cases where they are superfluous, such as in the following. For this non-zero non-terminal, there wasn't really any chance of us misinterpreting what the 1, 2, 3, etc. would be. But if we're going to have these two rules as part of a common grammar, then we really should be consistent and use single quotes everywhere. Next, I'll be using extended BNF to define a grammar for expressions supporting addition, subtraction, multiplication, division, and even exponentiation, as well as nested expressions inside of parentheses. Furthermore, we will make sure the grammar defines operator precedence. Here is a version of an extended BNF grammar for such expressions that uses the clean star and internal selection and puts all terminals in single quotes. Note in particular that we allow parenthetical expressions, and these parentheses are in single quotes, whereas these parentheses are part of the EBNF set of symbols we are using to define the grammar. We also have our identifiers and literals, which, once again, we're treating them as terminals, so we're putting them in quotes, even though we won't literally have the word ID or the word literal in the grammatical expressions. Of course, instead of using the clean star notation, we could use the alternative EBNF notation we saw before that uses curly braces, which would look like this. Note that in this version of the grammar, I've opted not to use single quotes to identify the terminals. Since I'm no longer using a clean star to represent repetition 0 or more times, there's no ambiguity for this asterisk, which is multiplication. Now, we could say that there's still some ambiguity with these parentheses here, because parentheses are used for nested selection up in these rules. However, there is no vertical selection bar here, so we'll assume that it's clear what I mean. In any case, these do represent the same grammar. To see how this grammar indicates operator precedence, let's create a parse tree for this expression. And I'll be doing this upside down as I did in a previous video. First, we will identify all of the literals and identifiers. Note that I've used the word lit instead of literal simply to save space. So everything that is a literal or an ID is actually an EXP. So now we'll do that for all of these symbols. Here's where things start to get interesting. The only rule that has an EXP on the right-hand side is factor. And a factor can either be an individual EXP or one followed by a caret for exponentiation and another. So we can go through this and identify the places where there is a caret. However, this caret is next to parentheses, and so that will not match this rule yet, because we have multiple separate EXP instances and not a single in this left-hand position of that caret. However, we can simplify this to an individual factor. We can also simplify most of these EXPs to individual factors, but we're going to have to leave this one open because it will eventually be part of a factor that involves this caret. Now that we have factors, we can look at rules that have a factor on the right-hand side. The only such rule is term, and term will either have an individual factor in it or will be responsible for multiplying or dividing two factors. So if we see multiplication or division with two factors side by side, we can simplify that, and that is something that we see here and here. So each of these will become terms. And although we see multiplication here, we can't simplify this until we make this entire entity in the parentheses into a factor in its own right. So at this point, we're not looking for any more factors that include a multiplication or division, and we'll simply be turning all of these factors, except for this one, into standalone terms. Now that we have terms, we can simplify things into expressions. So an expression takes two terms and that have a plus or a minus between them, or simply converts a standalone term into an expression. So here is an example where we have a plus. We have a minus here, but the thing on the left-hand side is in parentheses, so we won't be able to simplify that yet. And we also have a minus here, and because we've thoroughly simplified the left and the right of that minus, we actually can simplify this into an expression. We have a term followed by a minus terminal followed by a term, and so this whole thing will become an expression. And we'll simplify this as well. Now that we have expressions, we get to loop around back to the bottom of our grammar, sort of respect the recursive aspect of it, and absorb the parentheses that are out here. So these parentheses will be absorbed into an EXP, as will these. The other ones are going to have to wait until we simplify the other components. But here's what happens when we absorb those parentheses and these parentheses. So we've gone full circle through the grammar, and we've gotten back to EXP again. But not everything is simplified. However, at this point, we can start simplifying some of the things we missed the first time through. For example, now we have an exp next to an exp with a caret between. This will allow us to apply this rule, turn it into a factor, and finally simplify this part of the tree. Now that we have a factor here, we can simplify this to a term, and then once we have a term plus and a term, we'll be able to simplify this whole thing into an expression. At this point, I don't have any more room to show the rules on the screen, so I'm going to focus only on the tree. But we are getting close. This expression, once we get rid of these parentheses, will be part of an exp. An exp is a factor, and a factor can be multiplied by another factor, and all of those components are subsumed by a term. So now we have an exp, a minus, and then a term. So if we can simply get this side to be on the same level as this, we'll have two terms, one minus the other, which will be an expression. So an exp is a factor, which is a term, which can be part of an expression if we have term minus term. And that is the finished tree. The structure of the tree indicates the order of the operations and thus the operator precedence. Things that are closer to the leaves have to be simplified first. We can't simplify this sub-expression into a term until we calculate what this is. Only once we have that term can we include it in an expression that involves subtraction. And only once we've simplified all of this sub-expression in the parentheses will we have an exp, which can be turned into a factor and then incorporated as part of this term in that multiplication operation. So our grammar has successfully specified the order of operations. Unfortunately, this nice EBNF grammar is actually ambiguous. In particular, EBNF does not specify the associativity of operations, which is not an issue that we saw in this expression. Associativity basically determines whether we compute operations from left to right or from right to left. Here I have two copies of the same expression. What should the parse tree for this expression look like? Here are two options. These parse orders have different results, but we know that left to right is the correct order. Here are the results we get in these two cases. If we go from left to right, adding up the items and then eventually subtracting them, we'll get 12. This is the correct answer. However, if we do 4 minus 1 first to get 3, then 6 minus 3 to get 3, and 8 minus that 3 to get 5, and then continue from the right side, adding along the way, we'll get 20. This is wrong. Our EBNF grammar doesn't make it clear that we should do this instead of this. The way that you would specify the order of operations with standard BNF is by being very careful in how you order the recursion, like so. This particular grammar rule uses recursion and has an expression being equivalent either to another expression, then the operator, then a term, or a standalone term. This is the base case. Because the expression is on the left side of the right-hand side definition, this is known as a left recursive definition, which therefore makes it left associative with respect to these operators. If we had had a term here and an expression here instead, then it would have been right recursive and would have forced right associativity, which would be wrong. Now, sometimes we actually do want an operator to be right associative. In fact, the exponent operator should be right recursive, like so. So this recursive definition has a factor being an expression raised to a factor or a regular expression. Because factor is the recursive definition here, and it is on the right-hand side, this is right recursive and causes exponentiation to be right associative. Unfortunately, left recursive definitions have certain problems. But fortunately, with extended BNF, which is on its own ambiguous, there are ways outside of the grammar itself to tell the compiler what the associativity of a given operator is. So, we can keep using extended BNF as long as we keep in mind that we have to have a notion of what the correct associativity is independent of the grammar itself.